For this lesson, we're going to talk about the simplest type of organic compounds. They're known as hydrocarbons, and these are compounds that consist solely of carbons and hydrogens. Recall that carbon atoms usually have a bonding capacity of 4, meaning that it needs 4 bonds or 8 electrons in order to satisfy the octet rule, whereas hydrogen only needs 2 electrons or 1 bond to satisfy that octet rule. There are 3 different types of hydrocarbons. The first one are saturated hydrocarbons, and they're known as alkanes. They're saturated because they only have single bonds. So the carbon bonding capacity is still 4. Hydrogen, it will always be a bonding capacity of 1 or 2 electrons. When it comes to alkanes, it has the suffix ane. It has the formula CnH2n plus 2, where n represents the number of carbons. So n represents the number of carbons. So if our hydrocarbon only has one carbon, we'll use the prefix meth and add it to the suffix anes. So it becomes methane. If our hydrocarbon or organic compound consists of 2 carbons, then the name of that single bonded organic compound is known as ethane. So our prefixes here always come before the suffix ane. And that's dependent on the number of carbons. 1, 2, 3 is prop, 4 is bute, 5 pent, so 5 carbons, 6 hex, 7 hept, 8 oct, 9 non, and 10 dec. So if you have 10 carbons in your organic compound that only consists of hydrocarbons and they're all single bonds, then the name of that compound is decane. The next type of hydrocarbons we have are unsaturated hydrocarbons, and they contain at least one double or triple bond. So you don't have a fully saturated compound where all of the carbons are single bonds. The first type of unsaturated hydrocarbon is an alkene. So straight off the bat, all we're doing is just changing the suffix at the end. We had ane, now we have ene. The ene represents that you have at least one double bond in your hydrocarbon compound. The formula is slightly different. The n variable still represents the number of carbons, but the formula is CnH2n. So it's still dependent on the number of carbons. So we're still going to use these prefixes as part of the nomenclature or the naming system. We also have alkynes as part of our unsaturated hydrocarbons. It consists of at least one triple bond, and therefore it will have a different formula. It is now Cn, so it's still dependent on the number of carbons, but the H has the formula of 2n minus 2. If we have 2 double bonds in our organic compound, our hydrocarbon, then it's known as a diene, but it's not limited to having those 2 double bonds in a row. As long as you have 2 double bonds in the whole entire compound, you would have a diene, 2 enes, 2 double bonds. If you had 3 double bonds in your organic compound, not necessarily in the same, like consecutively one after another, now you have trienes. You have 3 double bonds. The last type of hydrocarbons is kind of like a combination of a ring and an unsaturated carbons. And these are known as aromatics because typically in the industry, they are responsible for a lot of the scents in the perfume industry, actually. So aromatics. And most of them contain what we call a benzene ring. So it does have a connecting kind of cyclic structure. So a closed ring. where you have alternating double bonds. So double, single, double, single, double, single. Um, it is going to be a type of unsaturated hydrocarbon, but it's on a league of its own because it's in a closed ring and because of the repeating pattern of the alternating double bonds. Because this is a common type of hydrocarbon, we actually draw it with still the same number of carbons represented by the vertices here in your geometric structure. Because it is a 1, 2, 3, 4, 5, 6 member ring, we do draw the hexagon, like the polygon shape, 1, 2, 3, 4, 5, 6. The alternating double bonds, we just draw a circle, which represents that you can have a resonance structure. And remember, grade 12's resonance structure is just moving those double bonds. Those double bonds are, again, just electrons, 2 electrons. And you can have your double bond here, which means that this double bond is moving here or here. So this is equivalent to having a hexagon, still your 6-member ring. We're not making any carbon or hydrogens disappear. We still have our hydrogens out here, and they're all 1 hydrogen per carbon. So that doesn't change. But when this is in resonance with another structure, it's because all we're doing is changing where the double bonds are. We're still going to have the same pattern, alternating pattern. So instead of having the double bond here, we're going to have it at the top. Instead of this one on the top right, we're just going to have it on the bottom right. And then this gets pushed to the left-hand side. It still has an alternating pattern of double and single bonds all around. So instead of drawing both of them, we can just draw this simple symbol. We have a naming system or a nomenclature for coming up with the names of all of these hydrocarbons. The first thing we have to recognize based on the structure is what types of bonds do we have. If we only have single bonds, then we have to use the suffix "ane" for the alkanes. If we have only double bonds, we have to use the suffix "ene," E-N-E, for alkenes. And if we have 2 or 3, we have to use the prefix "di" or "tri." If we have 4, we'll use tetra. So there are 4 alkenes, 4 double bonds. If we have 1 or more triple bonds, we have to use the suffix "ine," Y-N-E. The next rule is to determine the longest carbon-carbon chain. And we either call that the parent chain or the main chain. Anything branched off from that are known as substituents or functional groups, but we need to recognize what is the longest carbon-to-carbon chain. If there is a double or a triple bond present, so a double bond between 2 carbon atoms, and same for the triple bond, we need to incorporate that in our main chain. The next rule is to attach a prefix that corresponds to the number of carbons. And remember, we already learned our prefixes based on the number of carbons. We have to add cyclo to the prefix if it is a ring structure. So if it doesn't have that unique alternating double bond pattern in a ring, it's not going to be considered an aromatic or a benzene ring. So we have to use actually the prefix cyclo to represent that it is a cyclic structure. If it follows the regular straight carbon-carbon chain, we just name it as is. We probably won't go over N as a prefix. ISO is something we will go through a little bit later. The next rule, assign numbers to each carbon of the parent chain. So we need to make sure that we're ordering them correctly. So if you have a long carbon-carbon chain, you either start left and then left to right or right to left. For alkenes and alkynes, the first carbon of the multiple bond should have the smallest number. So you want to order such that you have the lowest combination possible. Now, the main parent chain, which only consists of carbon, So carbon to carbon to carbon doesn't necessarily have to be this like horizontal linear chain. You could have like a different combination as long as it's carbon to carbon. For alkanes, the first branch should have the lowest number. So if something coming off of your main chain or your parent chain, you want to order it such that that functional group you get to that functional group sooner. The fifth step is determine the correct name for each branch. So if you do have a branch off of the parent chain, you can have substituents attached to it and they can have different numbers of carbons because after all we're talking about right now are hydrocarbons. Only organic compounds with carbons and hydrogens. So you're still following that prefix, but now it's just a general alkyl group and not part of your main chain. Number 6, attach the name of the branch along with its carbon position to the name of the parent as a prefix. So if you do have a branch, you're going to add that branch, depending on the number of carbon, to the main chain. If you have you have to represent the location number off of your main chain. We're going to separate the number from words with hyphens. So technically, if we name them, it's all one word. We're just trying to separate the numbers from the letters. And we'll see that in action when we go through a couple of examples. Number 7 is list branches alphabetically when more than one branch group is present off of the parent chain. So if you have multiple branches, just like off of a tree, for example, for us in our naming system, because we have different branches to sort of put them in an organized manner, we're going to put them in alphabetical order when naming it. Number 8, when 2 or more substituents are identical, we're going to use an additional prefix. 2 for di, 3 for tri, 4 for tetra. Just like if we have 2 double bonds or 3 double bonds, if we have 2 of the same substituent off of the main chain, then we can use these prefixes. When it comes to naming, these prefixes, di, tri, and tetra, are actually ignored when it comes to determining the alphabetical order of your branches or your substituents attached to your main chain. The last and final rule is when identical groups are on the same carbon, repeat the number of this carbon in the name. We always want to number where that substituent or that branch is off of the main chain. So let's see all of these rules in action by looking at a couple of examples together. We're going to use those rules and apply them to alkanes. And remember that alkanes are just hydrocarbons that contain carbon and hydrogen atoms, but are all in single bonds. Our first example here, and I'm always going to go through the example, and keep in mind we'll always have the rules on the left-hand side. For our first example, we're presented with the actual complete structural formula, where we have not only just the carbon-carbon bonds, but we also have the carbon-hydrogen bonds. Remember that carbon, when it comes to the saturated type, all single bonds, there are always going to be 4 bonds around the carbon in order to satisfy that octet rule, 2, 4, 6, 8. This carbon over here obeys that octet rule with the 8 electrons. So this is the complete structural formula because it includes all bonds. From this point on, though, we will only look at the condensed structure, only because we know that carbon, if not attached to another carbon atom, will by default be filled with hydrogen atoms. Our focus when it comes to naming is also based on the number of carbon atoms. So this is the condensed structure, and then this is the complete structural formula. The condensed structural formula still has CH3, but again, just directly attached to the carbon. We know that they're all separated and individually bonded to that carbon and that carbon atom. This carbon is also attached to another carbon, so that represents this bond here. So it's carbon to carbon still. with hydrogen atoms attached to each carbon atom. So we're going to apply the rules in figuring or determining the name for this organic compound. We have 1, 2, 3 carbons or 1, 2, 3 carbons. Based on the condensed, we can see that nothing else is attached to it besides the hydrogen. So by default, the longest chain has to be this right here, carbon to carbon to carbon, where there are 3 carbons on your main chain or your parent chain. They're all single bonds. So we're going to use alkane or ane as the suffix. Our longest carbon to carbon chain has 3 carbons in it. So I'll write that down, 3 carbons. We're not going to add a prefix besides the number of carbons because it's not cyclic, nor does it actually have any substituents attached to it, just because it's all just hydrogens. So in order to name this, all we have to acknowledge are the number of carbon atoms, 1, 2, 3, or we can simply use the condensed structural formula, 1, 2, 3 carbons, and therefore 3, the prefix that we use is prop. So when we add in prop, as well as all of them being single bonds, the suffix ane, the name becomes propane. All one word, propane. And those are actually your barbecue tanks. It's filled with propane gas, which are just a bunch of C's and H's. The line structure is a lot more simpler than the complete and as well as the condensed formula. Instead of writing all of our carbons and hydrogens, we'll represent the edge or the vertex as our carbon atoms. We kind of neglect the hydrogens because, again, really, they're just filler atoms for our carbon-carbon chain. So if we see our single bond here, it's slightly bent only because, remember, we still want to spread these bonds as far apart as possible in 2D space because these bonds all contain electrons, all negative charges that want to avoid each other. So it has this kind of bent shape. So I'll just kind of rotate it and just draw it like this, kind of like a mountain peak, where this terminal end and this terminal end both represent carbons. Carbon, carbon, and this vertex here also represents the middle carbon here. This is our line structural formula for propane, 1, 2, 3 carbons. But we know already that the carbons it doesn't just have one bond at the terminal ends. There's still going to be 3 hydrogens in order to satisfy the octet rule. We just don't really acknowledge it. We just know it's there. Since this organic compound has no branches coming out of it, if I highlight it over here or here, there are no additional carbon chains coming out of the main chain. It doesn't have any substituents. So it's just taking into account a prefix acknowledging the number of carbon atoms along your main chain, and then acknowledging what type of hydrocarbon do we have. And because they're all single bonds, it's ane, so propane. For our next example, we're given the name and we have to determine the condensed structural formula as well as the line structural formula. This is known as the IUPAC name, and it is the same system that we've been using. We have to follow these set of rules in order to derive to the correct name for that organic compound. Now, IUPAC stands for the International Union of Pure and Applied Chemistry, and it's universally acknowledged such that any scientist worldwide will still use the same system. So pentane is the organic compound that we need to look at, and we're going to dissect it we're going to actually dissect the name. At the end, which is our suffix over here, has the root ane, A-N-E, which means that we have an alkane, all single bonds. How many carbon single bonds do we have? Well, we have the prefix pent. And pent stands for 5 carbons. And because we're in control of actually drawing the structural formula, we're just going to draw 5 carbon atoms in a row. Don't forget to leave yourself a little bit of room in between the carbon to carbon bond because we still have to draw our hydrogens. 1, 2, 3, 4, and then this is our 5th carbon. We're in control of it. Why not just draw it in a linear or horizontal manner, left to right? Now, this is not the complete condensed structural formula. We still have to draw the hydrogens. So we have only 1 bond here, but we know that carbon should have 4 bonds. That means that 3 out of the 4 bonds are actually individually bonded to hydrogen atoms. So to acknowledge that, we're just going to write H3. So this carbon is bonded to 3 hydrogens and 1 carbon for a total of 4 bonds. This this carbon here has 2 bonds. So we need to just draw 2 hydrogens to have a total of 4 bonds for this carbon. 1, 2, 3, 4. It's the same story for anything in the middle. So this carbon, 2 bonds. So we need 2 hydrogens to make up the remaining 2 bonds to make a total of 4 bonds for this carbon atom. Same thing over here. And then the last one, because it is at the terminal end, it only has 1 bond already. So we have to make up for the 3 remaining bonds for a total of 4. Remember, 4 bonds for carbon. So we have to draw 3 hydrogens. Now notice I wrote the hydrogen at the beginning over here. It doesn't matter if you were to write CH3 or H3C. What we know is that this carbon is bonded to this carbon, but also 3 hydrogens. So it doesn't matter if you write a H3 here or H3 here. You acknowledged it both ways. So it doesn't really matter. Here, I just drew the H3 here because I know this is a carbon to carbon bond. Even though we have hydrogens in the way, we know that they're actually directly attached to the carbon. For the line structural formula, because geometrically speaking in 2D space, we still want to avoid all the hydrogen atoms. Even though we don't draw them directly in our line structural formula, we're still going to adapt that kind of like mountain peak type of design. So over here, because we have 5, we're going to start off at the bottom here. And remember, vertices and terminal ends of our mountain peaks, if you will, represent a carbon atom. We need to draw 5 carbons. So we'll start off here, 1, 2. So right now we drew 2 carbons, 1, 2, 3. 1, 2, 3. Looks very similar to our first example, but we need to draw 2 more, 3, 4, 5. Start from the bottom and draw your mountain peaks. Every time you have an odd number of carbons, you always complete the mountain peak as if it's a whole mountain. So you have 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Remember our line structural formula, we don't actually include the hydrogens in the design, but they are there. For our third example, we're given the line structural formula. So we need to follow the rules here, the naming system or nomenclature, to determine the name. And we can also draw the condensed structural formula based off of the line formula. All we have are single bonds, and these are all carbons. So I'm just going to remind you that the vertices and the terminal ends are all carbons. So I'll draw them in red. So this is a carbon, 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 and carbon. Since they're all single bonds, we know that the hydrogens are there, but they are invisible in the line structural formula. We are dealing with alkanes. So it will, at the end of the main chain or the parent chain, will have the suffix ane. We now need to determine the longest carbon-carbon chain. So we can move from 1, 2, 3. That's one option. 1, 2, 3, 4. Or 1, 2, 3, 4, or 1, 2, 3, 4. The longest carbon-to-carbon chain that we've noticed is 4 carbons in a row. It has to be carbon to carbon in order to be considered as part of the parent or main chain. Visually, I'm just going to put 1, 2, 3, 4, this as our main chain. I could have easily done 1, 2, 3, 4. That's perfectly valid, and they're both equivalent to each other. But I'm just going to do this just because it looks easier. It's easier visually speaking. All right, so our longest chain is a 4-membered ring. We're going to attach a prefix that corresponds to the number of carbons in the parent chain. There's no cycle or there's no ring in our carbon-carbon chain. It's just a straight linear chain, 1, 2, 3, 4. Because we have 4 carbons, and I'll write it down here, we're going to have the prefix but, B-U-T. And because we have single bonds all around here, it'll be butane as our parent chain. We have something coming off of our main chain. It's not just a regular linear chain. We do have this carbon coming out. So that carbon becomes part of your substituent or a branch. So I'll just, let me highlight that in a different color. We're going to assign numbers to each carbon of the parent chain because it matters now. There's a branch coming off of this carbon. For alkanes, the first branch should have the lowest number. So now that we've highlighted our main chain in our blue color, we can either number it starting from this end or the right side, this end. We can number it 1, 2, 3, 4, or we can number it starting from right to left, 1, 2, 3, 4. We want to make sure, because this is our only branch or substituent, and let me spell I will not spell it up there because we have to come up with the condense here. Substituent. So an add-on or a branch is coming off of this carbon. We want to hit it such that it approaches at the lowest combination possible, the lowest carbon number. If we were to number it from left to right, the carbon location would be at the second carbon location. So 1, 2, 3, 4. If we were to number it such that we start from the right and then proceed to the left, and I'll just draw it at the top over here, 1, 2, 3, 4, this would be carbon number 3. That's a higher number. So we have to read it from left to right because we have a lower carbon location. So that's what they mean by the lowest number. It's 1, 2. So we're reading left to right. They're both still 4 carbon member rings. It's just this is the lowest combination carbon possible. So this is the lowest location. So I'm going to erase the blue ink just because that's not the order that we're going to use. We need to determine the correct name for each branch. So the branch over here only contains 1 carbon. Because it only contains 1 carbon, we're going to use the substituent name methyl. So this is methyl. Attach the name of the branch along with the carbon position, along with its carbon position. So the carbon position off of the main chain is position number 2. We put a hyphen to separate the number from the words. So we have 2-methyl. What do we have on the second carbon off of our main chain? Just 1 carbon. We're going to list the branches alphabetically because this is the only branch. There's nothing else coming out of it. So it's just, by default, the only branch, 2-methyl. We don't have 2 or more substituents, and we don't have identical groups on the same carbon. It's just 1 branch. So when we put all of these components together, so the branch, as well as the main chain, we combine them into 1 name. The final answer is 2-methyl butane, all 1 word, because it is a single name. We put our substituents at the beginning, and our last word here, or our last part, or our suffix, will always be part of that parent chain. 2-methylbutane. To draw the structural formula, we just have to follow the main chain first. So I'll just draw that in red. All carbon, 1, 2, 3, 4. So C2, 3, 4. And at the second carbon, 1, 2. So because we're in control of drawing it, might as well draw it from left to right as it's drawn in the line structural formula. So 1, 2, we have a carbon attached. This is not the complete answer for the condensed structural formula. We have to draw all of our hydrogens. We have 1, 2, 3 terminal ends. They will always have CH3, CH3, and CH3 in order to maintain that octet rule. 8 electrons or 4 bonds around the carbon atom. 3 for hydrogen, 1 for another carbon. This over here, this carbon has 1, 2, 3 carbons attached to it. 3 bonds. It only needs 1 more bond to satisfy the octet rule, so we're just going to draw 1 hydrogen. Unlike over here, this carbon is attached to only 2 carbons. So the other 2, the remaining 2 bonds must be with hydrogen. So it becomes CH3, CH3, CH3 here, whereas the T over here, carbon number 2 off of the main chain, has 3 bonds, so it's just CH. Carbon number 3 has a CH2, and then, of course, carbon number 4 is CH3. For our next example, we're given the condensed structural formula. Since we're only dealing with single bonds, we're going to have the suffix for the parent chain as the ane for our alkane, so ane. Now we have to determine the longest carbon-carbon chain. Now there are different possibilities because we can go 1, 2, 3, 4, 5, 6, so 6 carbons versus 1, 2, 3, 4, 5, 6, another long carbon chain versus 1, 2, 3, 4, that's too short, or 1, 2, 3, 4, 5, 6. Because we can control, just because if we were to go into carbon to carbon to carbon, and then over here, we would still have 6 carbon chains, but then we would have this 3 carbon kind of branch off of the second position. It's not going to be like linear. So I think for now, it's easier just to name it, number it as 1, 2, 3, 4, 5, 6 linearly. It could be the same if you decided to have this as your terminal carbon, but I'll just do it from 1, 2, 3, 4, 5, 6. So this is our main chain that I'm highlighting. Anything that comes off of that main chain is considered a substituent. So we have a substituent here, here, and then here as well. All right, so we need to dissect a little bit more of our main chain. We're going to attach a prefix that corresponds to the number of carbons in the parent chain. So this is our longest carbon to carbon chain, 1, 2, 3, 4, 5, 6. So we have a 6 carbon ring, 6 carbon main chain. So 6 carbons is equal to hex. And because it's all single bonds, it's hexane. So we're going to have for the IUPAC name, the parent chain at the end, hexane, with 3 substituents coming out of it. Now we have to number it such that we have the lowest combination of possible. Because we have our linear chain, we can only number it from left to right, or from this terminal end, right to left. So I'm going to draw the left to right in blue, and we'll see what combinations we have. We have 1, 2, 3, 4, 5, 6. So if we were to follow left to right, our substituent combinations would be at the third carbon, followed by the 4th carbon, and then the 5th carbon. If we were to number it right to left, we would start here with 1, 2, 3, 4, 5, 6. Our branches will come off of carbon number 2, 3, and then the fourth one. So the lowest combination possible would be 2, 3, 4 instead of 3, 4, 5. So we're going to follow the red numbering order where we're reading from right to left. So this carbon here is coming off of the second carbon instead of the fifth. So I'm just going to erase the ones in blue because those are not the correct order that we're going to use. Now that we established the order, we can determine the correct name for each branch. So we're going to use 2, 3, and 4. Because we have from the second a methyl, well, one carbon. So at the second, I don't know, I don't have room. I'll just write the 2 here. 2, the second carbon position, we have one carbon, we'll have the name methyl. So this is for the second position. We have one carbon, so 2-methyl. First, second, at the third position, the third carbon off of the main chain, we have a 2-carbon branch. For 2-carbon branch, we have the substituent or the name ethyl. At the third carbon, we have ethyl now. 1, 2, 3. And then at the fourth carbon position, so 4 here, we have one carbon again. So we're going to be using methyl. So at the fourth carbon, we have one carbon, so 4-methyl. We attach the name of the branch along with its carbon position, which we did. So this is the carbon positions, and these are the type of substituents you have attached, the types of branches. We need to separate the number from the words with hyphens. So this is your hyphen. We're going to list the branches alphabetically when more than one branch group is present. So we have E and M. E versus M. We're going to name our ethyl first when it comes to the full, complete IUPAC name of this organic compound. So this is the first substituent, even though it's not at the first carbon position. It's not in numerical order, it's in alphabetical order. So E versus M and M as well. When 2 or more substituents are identical, we're going to use the prefixes di, tri, and tetra. For us, we have at carbons 2 and carbons 4, we have the same exact substituent, methyl and methyl. So we're going to use 3-ethyl, but also, because we're going to use these two, we're going to use 2 and 4-dimethyl. So we're going to use dimethyl. Note that the prefixes are ignored. So even though you have this prefix di, it's still going to be E versus M. So we're still going to write that ethyl first. When identical groups are on the same carbon, which we don't have because they're at different positions, we don't need to follow 9. But we need to still acknowledge that these 2 methyl groups are at different positions. The positions are 2 and 4. So 2 and 4. We still have our dash here, but it's not 24. It's not at the 24th position, so we put a comma between 2 numbers. When I combine all of these components together to make one name, we're going to use 2,4-dimethyl. We're going to use 3-ethyl as well as our parent chain hexane. We're going to combine them all together to make one single name. We need to go in alphabetical order when it comes to our substituents. So we're first going to write 3-ethyl. Because we have a number afterwards, because this is our next chain, our next substituent, we have to write a hyphen here, a dash. 3-ethyl, 2,4-dimethyl, and then our final parent chain, hexane. All one word. some of the numbers and the words, they're just going to be separated by these dashes. But if you have numbers, you separate them from commas. Always have your substituents at the beginning and then your parent chain at the end. 3-ethyl-2,4-dimethylhexane. That's the IUPAC name for this compound. To draw the line structural formula, always start off with your main chain. Because it's a 6-member ring, I'm going to draw 6 carbons. Remember that we use that mountain peak kind of design. So we start at the bottom, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. You can go in the same order because we read it from left to right. 1, 2, 3, 4, 5, 6. It's still a 6-carbon chain. So if we were to follow it based on the given condensed structural formula, not at the first carbon, but the second carbon position, we have a methyl. So 1, 2. We're just going to draw a line here. This represents the 1 carbon here, because remember, vertices here or terminal ends represent carbons. We just don't acknowledge that hydrogen. Even though they're there, we don't draw it in. At the third carbon position, so the third carbon along your main chain, you have an ethyl group, 2 carbons attached to it. So 1, 2, 3, we have 2 carbons. So I'm going to draw one line here. This represents just 1 carbon. We need to draw another one. But remember, we do have hydrogens. They want to avoid each other as much as possible. We're going to just bend that bond exactly how we bend it over here. Just over here. Oh, that looks like a double bond. Let me just redraw it. Just a straight line. So you have 1, 2 carbons. 2 carbons off of carbon number 3. At the fourth carbon position along your main chain, you have 1 carbon, a methyl group. So we're just going to draw it down here. This is still going to be your main chain. 1, 2, 3, 4, 5, 6. You just have 3 substituents coming off of the main chain. For the last example, we're given the IUPAC name, and now we have to draw the formulas. We always start off with the parent chain, which is heptane. Heptane stands for 7 carbons. It's all single bonds. Don't forget to leave yourself enough room for the hydrogens that we fill in last. So 1, 2, 3, 4, 5, 6, 7. Don't draw your hydrogens in yet because we actually have branches or substituents coming off of the heptane main chain. So we're done that. We have at the 5th position a propyl, and at the 2nd and 4th carbon off of our main chain, we have a methyl. So we have 2 methyls, one on the 2nd, the other one at the 4th. So if we number this as our first carbon, because we can control how to draw it, might as well draw it left to right. 1, 2, we have a carbon attached to it. So we have carbon here. 1, 2, 3, 4. 1, 2, 3, 4. So we have another methyl. We're done with that. The last substituent is at the 5th carbon, and it is a propyl. Propyl means 3 carbons, 3 C's. So 1, 2, 3, 4, 5th position, 5th carbon, we have 3 carbons attached to it. So 1, 2, 3. We're not complete in our condensed structural formula. We have to fill in the rest with our hydrogens. So every time you have a terminal end, it's always going to be CH3 because you need to have 4 bonds around the carbon. And at the terminal ends, we only have 1 so far. So 1 here, so therefore CH3 to make 4 bonds. When you're in between, it depends on how many bonds you have to begin with. In this case, we have 1, 2, 3 bonds, so we need only 1 hydrogen to have 4 bonds around the carbon. Here, we need just 2, just 1, and 2. So this is our condensed structural formula. Oh, I forgot my CH2s here. 1, 2, so 3, 4, so CH2. To draw our structural formula, again, we start off with our main chain, a 7 carbon linear chain. So 1, 2, 3, 4, 5, 6, 7. Okay. And at the second and the 1, 2, 3, 4, and the fourth, we have a carbon. And then at the fifth, we have a propyl, so 3 carbons. So 1, 2, and I'll go down here maybe 3. Make sure you're acknowledging the invisible hydrogens. For this example, we have a 7 carbon chain. Now, this is the longest chain I've identified. We could have also chosen 1, 2, 3, 4, 5, 6, 7, but they are equivalent. We have to determine the order. We know that it is a heptane because it's a 7 carbon chain, but we're going to number it from left to right, where this is our first carbon, and we're going to follow through until we get to the 7 carbons accounted for. The reason why we're going to number it left to right is because we get to our substituents or branches off of our main chain sooner when we write it from left to right. It's at the second position and the fourth position. If we were to do it right to left, we would have higher location numbers off of our main chain. Our first substituent here at the second carbon is just 1 carbon. So it is 2-methyl. Second position, 1 carbon. At our fourth position, we have a unique substituent, a unique branch. We do have 3 carbons. So at the fourth position, the fourth carbon, we are going to have 1, 2, 3, a propyl group. But because it's not going to be attached at the first carbon and like just followed linearly, it's actually attached to the second carbon off of our propyl branch or substituent here. We need to rename it as isopropyl. So when you put it all together, it's 4-isopropyl. It's different from our normal attachment of just a straight carbon to carbon to carbon. So it's isopropyl. This becomes the actual name. So it does become part of your alphabetical order when you're considering how to name this compound. So when you put all of these components together, the 4-isopropyl, along with the 2-methyl and the heptane, we're going to take into consideration our substituents of I before M. So when you put it all together, it becomes 4-isopropyl dash 2 dash methyl heptane. The line structural formula will just be based off of the condensed one. So start off with your main chain, 1, 2, 3, 4, 5, 6, 7. The second one, we have 1 methyl group, 1, 2. And then at the fourth position, we have our isopropyl, where we have a carbon, which is this carbon here, and it splits up into another carbon and then another carbon here. For our last alkane single bond example, our main chain will be our linear part here, but because it is carbon to carbon, our main chain will also include this carbon here for a total number of 1, 2, 3, 4, 5, 6, 7, 8 carbons. Since you have 8 carbons, it will have the main chain as an octane. Anything coming out of that main chain will be your substituents. If we were to number it left to right, we would have the substituents at locations 3, 4, and 5. 6, 7, 8 are the rest of them. If we were to reverse the order and start here from right to left, we would have it at positions 1, 2, 3, 4, 5, and 6. So the combination of 3, 4, and 5 is lower. So we're going to go from left to right in terms of our numbering order. 3, 4, 5 instead of 4, 5, 6, 7, 8. Okay, so at the third location of our carbon, we have the substituent. So 3, we have a methyl group. At our fourth position, we also have a methyl group. At our fifth carbon, we have 2 methyls. Whoops, over here. So you have two methyls. So at 5 and 5, we have two methyls, so it's a dimethyl here. But notice all of our substituents here, 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 and here, all four of them are actually methyls. So we need to change our prefix because we have four of them at different locations, carbon locations. We have to change it to tetra or four. So we have tetramethyl, where two out of the four of them are in the same position. And all we have to distinguish are the location numbers. So when we put methyl, so when we put all of these together, because we only have one single substituent, methyl comes first. It's the only substituent. We have to number all of the locations along the main chain. So we have first our three, we have one at the fourth, and then we have two in the fifth position, the fifth carbon. So we have to write it twice for a combination or a total of four methyl groups. So these are our positions. How many methyls do we have? We have four of them. So we're going to write tetramethyl. And these are all our substituents. So we just write our parent chain at the end, octane, all one word. 3,4,5,5 tetramethyl octane. When we draw our structural formula, let's just number it from 1 to 8, left to right. 1, 2, 3, 4, 5, 6, 7, 8. Our third, that's not our third. First, second, third. Our third carbon, we have a methyl. Same with the fourth. And then at the fifth, we have two methyls coming out of it. So 1, 2, 3, 4, fifth. We have one methyl here and one methyl here, all trying to avoid each other.